Let me know whether you're ready, and then I can start the time.
Okay, lovely. Uh, Good day, everyone. Hope you're really, really well. Standing in front of you, this is Team Dataholics representing the University of the Western Cape. So what we're here to present is an effective treatment recommender for reducing avoidable readmission. So this solution is based on, it's mainly based on our ground research on South African research, which reveals 35% of readmissions which are deemed to be avoidable. As this lady on the right is complaining that imaliam iyaphela, which directly means that my money is finishing. So our main solution is just to focus on saving South African money by directly allocating the health resources. So here it'll be the information which will be covered in the new slides, in the next few slides, which are the background, problem statement, data process, data model, finding, results, and proposed solution. So heading to the background and problem statement, Gabriela we take this part. Yeah.
Good afternoon, everyone. My name is Gabriela, and I'll be explaining the background and the problem statement for our project. So firstly, we have three main objectives for our project, which is examining influenza readmission rates. And from there, we examine the percentage of them that were avoidable so that we can recommend an effective treatment that reduces avoidable readmissions. Our problem statement is avoidable influenza readmissions strain hospital resources and increase cost burdens on families and insurance. So by reducing them, we lower these costs and alleviate the financial strain on these families as well as benefit the community health. Okay. And onto our solution approach as well as our benefits. So we'll be recommending an effective treatment upon first diagnosis so that we reduce unnecessary expenditure on ineffective treatments. So why influenza? So influenza is ranked 7th among diseases with the highest impact in South Africa. This ranking is based on mortality as well as infection rates. For contagious diseases, it's preventing contagious diseases is best solved by proactively acting on them by avoiding avoidable readmissions. Hence, we need a target and treatment that is correct at first diagnosis. So why AI? AI will be monitoring the procedures and other variables amongst readmitted patients. For example, it might infer treatment resistance and also evaluates treatment efficiency. And now we will be on to our data process, which will be presented by Kevin.
Good day, everyone. I'll be going over the data process and how we made our pipeline to make our model, which will effectively recommend will recommend the most effective treatment for influenza. So let me go through that briefly. So we're given two types of data sources. We're given proprietary data, which was provided by Altron Solutions, and we're given public data. So in terms of the proprietary data, this data was given to us in a SQL database, and it had a release. We handpick tables in the database which were related to our case. And then from this, we needed more demographic data about the patient. So we got information about the population of the province that patient may be in. The postal code is also related to the location of where the patient may be in, and the air quality of the location that person is in. So for example, in the Western Cape, they might have bad air quality. That may link to, that can be an indicator to influenza. So how that links is we use these two data sources in our pre-processing step. So this involved data aggregation. From the proprietary data, we aggregated the tables based on columns just to have a gigantic data set. And this data set was cleaned by our team. Then from that, features were engineered from that aggregated data set. So Evolution will go through the feature engineering and the data modeling in our solution.
Thank you, Kevin. So yes, I will be taking you guys through our data-driven approach to solving our problem, which in this case is reducing avoidable readmissions or reclaims in medicine. So looking at our engineered features, we had two initial engineered features which we thought would be extremely helpful in our model. First being reoccurring readmissions, and this is identified by two conditions. Sorry, and basically the first condition being a claim is made within 5 to 30 days of the previous claim, which indicates that it has been. Oh, sorry, and the second claim being that both claims belong to the same person. And, okay, and this will return a Boolean variable as one of our engineered features, just as an indicator of whether this is reoccurring. Our second engineered feature is avoidable readmissions. So after finding recurring readmissions, we want to filter those or look into those and see which ones were avoidable. So this also has two conditions in order to be classified as avoidable. First being that the readmission must meet the criteria for a recurring entry, and secondly, that it is not the last claim in the sequence. Now, given the data set that we had, there were not a lot of references as to what each claim sort of meant. So there was no explicit entry to indicate which ones were sort of cured the patient from that illness. So we took the last claim of that sequence with no other recurring entries within the next 5 to 30 days as an indicator that that final treatment ended up curing the patient of that illness. Okay, and leveraging these these engineered features helped determine avoidable cases, first of all, and secondly, knowing these avoidable cases and reoccurring cases, it's essential for training our recommendation model on recommending the top three best medication or treatments, for treating influenza. And now Gabriela will take you through the rest.
So after we have engineered the two features that are gonna help us with the modeling, we just wanna visualize what they look like in the data set. So figure A shows that 2.5% of people who were treated are readmitted. So that means that the treatment didn't work for one reason or another. And then the figure on the right, figure B, shows that 20% of those who returned shouldn't have returned. They were avoidable, meaning that the treatment was inefficient and there was a better existing treatment for them. We're just gonna quantify the financial burden of these avoidable readmissions. So the World Healthcare Organization assigns South Africa an average of 98 million rands for influenza treatments specifically. And if we do some simple statistic calculations, we will have an average of 500 or 500,000 rands that was lost, but that loss was avoidable. You might find this amount small compared to the budget that they assigned it, but let's take into accountability the if we have more diseases taken into account, like they have other avoidable rates, as well as if we take into account other countries that have larger rates of readmission and more diseases that are frequent in their populations, then we'll be able to quantify the accumulative loss in reassigning costs to the medical health care. And now onto the data modeling, which Varoshan is going to further explain.
Okay, so now the fun stuff. Firstly, in order to feed in data to our models and to ensure that the model effectively predicts recurring claims, we address the class imbalance. So as you've seen from the previous pie charts, that out of an entire sample or population, there's only a small percentage that's actually reoccurring claims. So if we had to feed our model that data as is, we would get a huge imbalance causing very inaccurate recommendations. So to handle this imbalanced data, we first used undersampling, or we undersampled our non-recurring claims, in which case we reduced the number of non-recurring instances to balance the data set, and vice versa for reoccurring claims. Instead, for reoccurring claims, we retained all of the instances of reoccurring claims to preserve critical information. Okay, and from our models, after feeding in the balanced data sets, we ended up with these two ROC curves. Now, I will not burden you guys with interpreting every nitty-gritty part of this, but basically, we tested two models. Sorry, yes, so two models, the XGB classifier and random forest classifier. From these two, if you look at I don't know if you can see my cursor, but at the bottom of figure C and figure D is an area value of 0.83 for figure C, which indicates that the XGB classifier has an accuracy score of 83%. And likewise for the random forest classifier has an accuracy score of 84%. Now there is a slight difference in statistics, I guess any difference is significant. Well, depending on the context, and in healthcare, well, an improvement is an improvement. So for our model selection, we ended up choosing the random forest classifier. A little bit more understanding into why we chose, or a little more overview into our models. So for each model, we use a variety of a combination of features. And for the XGB classifier, we use previous procedure, which in that case is if a client is coming back for a recurring claim or treatment, we want to know what the previous procedure was that they were prescribed. Same with age, postal code, province, and suburb. So for the XGB classifier, what this diagram just shows or illustrates is that knowing the previous procedure is the most indicator of or feature that helped the XGB classifier to rank the top 3 treatments. As for the random forest classifier, you'll see that we have quite a few more features. However, the bottom few do not seem to show any indication. And the little black values on the side just is there to illustrate that those values, for the air quality index, temperature, humidity percentage, PM 2.5 and PM 10. Now these, you do not exactly need to know what each one is, but just that these relate to air quality for each region of a patient. And even though that they do not show up on the graph, they do affect the feature, the classifier's performance. And now for a proposed solution, which Vutomi will take you through.
So I'm just going to run you guys through the proposed solution we have. So our proposed solution that we have is a claim care app, which focuses on treatment recommendation, which is a web app. So it's used by medical practitioners, specialists, to educate them what is the best treatment to help our people. And it also empowers informed health decisions, reinforce trust in treatment effectiveness. So its functionality is that it uses an AI ranking model which recommends the most effective treatments. So it's based on user inputs such as personal ID, age, and geospatial data such as province, suburb, and town. Yeah. So I'm just gonna hop on to the solution that we have, which we bought on dot as a text. Yeah. So this is our solution that we have. You introduced with the declaration page, which you
The
have.
time is up. I'll give you 2 minutes to wrap up.
Sure. So wrapping up on our UI, which it's focus. It's very simple, and you can hop onto the recommendation classifier, which when you enter the personal ID, you select your age, your province, your suburb, your zip code, your disease, which is our focus, which is influenza. And you get the best ranked effective treatments on this. So we also have like the dashboard where we analyze the how these effective treatments, how we analyze how the cost, how effective these treatments are, like cost. So running around is that we have the cost structure, which it analyzes the monthly cost breakdown by member, by top 10 schemes, like top medical schemes. I mean, like, yeah. So it says this, so using this main member medical scheme, so the main member is the best. It shows that the main member scheme is the best medical scheme among them all. And for this one, we won't get into much because it's too much into financial statistics. So due to time, I won't go through that. But then we have shown like a coefficient matrix showing that how identifying this treatment and the scheme ID, which shows how cost effective this will help us. So improving